In this video, we are going to talk about something called the vehicle capability footprint or the vehicle footprint, or there's lots of different ways you can call it, but usually it's called footprint somehow, vehicle capability footprint or vehicle footprint. In general, for this video, we'll just call it the footprint. So, the footprint. So you might be asking yourself, what is the footprint? So the footprint represents all of the places on Earth that you can reach with your entry vehicle. So let's say, here's the Earth, and you've got, some, lines of latitude and such, like this. This is a 3D Earth. Yeah, this isn't a very good one, but should hopefully get the effect that I'm going for, these lines and stuff. So anyhow, if you are a spacecraft and you're flying in, you might be curious, where you can go. So imagine that, like, here I'll draw on the coastline. So if here's like the western United States, and there's the Baja California, and then there we go. There's Alaska and stuff like that, and here's Mexico and Florida and the East Coast and all that stuff. Here's Hawaii, for example. What this shows is you can show on the map where you can reach, and so it might look something like this. So for some types of vehicles, it might look like that. For other vehicles, it might look something like, something like this. Anyhow, the shape changes depending on your vehicle, but you might be asking, so what does this mean? So if we zoom over here, so think about this idea. So imagine here is our vehicle, and we're looking at it from the back as it's flying into the screen. And this direction up here represents up. And we talked earlier about how you can change the bank angle of the vehicle. Now the bank angle defines the lift, or the angle of the lift vector with respect to up. So here's the lift vector, and then here is the bank angle. And so what happens if you fly full lift up, as we've discussed before, you will fly the maximum downrange flown. And if you fly full lift down, so if you fly full lift down like this direction, you will fly the shortest downrange you can possibly fly. If you fly a little bit, lift right or lift left, you'll start getting these different locations. So if you say, okay, well, here's the lift down point where our spacecraft is, say up here, and the lift up point is down here, and our spacecraft is moving this direction. We say, okay, well, if we start varying our lift direction all the way around this circle, we start tracing out, if we start at the upper point, we'll start tracing out these points that look something like this. And we keep on going around the circle. We go all the way around. And if we connect all of these points, we get this kind of elliptical shape. And sometimes it's an ellipse, sometimes it's a different shape. It depends on what your vehicle is and how fast it's flying and how it's hitting the atmosphere. And it depends also on the lifting capability. And this shape is our footprint. So that's how you calculate it. You just take a whole bunch of bank angles and you take for your current position, and then you predict all the trajectories that result from all these bank angles if you go all the way around the circle. So in general, because it's, this is 0 degrees and this is 180 degrees, so you would say, well, we can go in 1 degree increments or something. So we can go, 0, 1, 2, 3, 4, 5, etc., all the way to 180. Then we have to do the exact same, going 0, -1, -2, all the way to -180. And that's a lot of, predictions. That's 360 predictions, because there's 360 degrees. So this isn't very good. So it turns out, if it takes a little bit of time to do each prediction, you don't want to have to wait to do 360 predictions. That'll take a while. So what you do instead is you can find locations along the edge of these footprints that do a pretty good job of describing the higher resolution footprint. So you could say, well, let's choose this point. We know that in general this is the maximum width point, and we could choose something like right here, and then maybe like something up here, and then maybe like a point here, like that, and then maybe this point down here at the tail as well as this point. And so we can come up and we can say, well, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is 10 points that pretty well approximate it, the true capability footprint, if we connect these with straight lines. This actually does a pretty good job of minimizing the discrepancy or minimizing the error between the true footprint versus this kind of approximated footprint. So we can we can pare this down to just be 10 predictions. So it all matters on how you select your bank angles, but the set of bank angles that I like using 0 degrees, which is full lift up. I like using plus or minus 15 degrees. That helps you define this area down here as you fly down. As you're coming this way, we call this area the toe, kind of going with that footprint analogy, and you might guess that this side is called the heel. And the heel and the toe are we kind of help use these terms to help guide ourselves. But anyhow, so we use the 0 degrees for the toe, plus or minus 15, and maybe plus or minus 30 degrees, and then plus or minus 45 degrees, plus or minus 60 degrees, plus or minus 90 degrees, and then 180 degrees. Now this is the exact same plus or minus 180 degrees, so it doesn't really matter. That's why we don't have to put the plus or minus. And the same thing here with 0, obviously. So this set is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this will be 12 predictions to do my footprint. And you can pick whatever bank angles you like to do, or you'd like for these, and you can use those to compute your footprint. So what does this really mean? Maybe you still are a little bit confused as to what this means. So if here's your footprint, and here's our vehicle flying up here, and we're going this direction, what this means is anywhere inside of this area you can reach by changing your lift vector. This area is, these outer edges define the area that you can barely reach. So you have to stretch out your capability to reach all the way down here, and you have to, max all the way down, to come to right here. So it means that if you vary your bank angle at all, you're going to stay inside of this area. So if your target, for example, is right here, if you're trying to land right here because this is where your boat is, your recovery forces and stuff, well, then I got some bad news. No matter how hard you try, you are not going to reach this. This is the closest point you'd be able to get to it. Likewise, if you have your target right here, that means, well, you're still too high and you're too fast and you haven't gotten rid of your energy. So the closest you'll be able to do is, fly down to here, whereas you would have flown to here before. So what this means is if you change your bank angle, you will end up somewhere inside of your footprint. So this is actually pretty cool. You can instead think of the problem of trying to get to your target. If your target actually is inside your footprint, that's a really good thing. So how you can think about it is, well, we just want to keep our target inside our footprint as long as possible, because another interesting thing is that the footprint is always shrinking. Footprint shrinks. And you might say, well, why is it shrinking? Well, let's think about where this footprint comes from. This footprint depends on things like, your velocity, and it depends on your flight path angle, which we call gamma, is your flight path angle. It depends on your lift to drag ratio, and it also depends on your energy level, which mostly is driven by your velocity. But this also deals with your altitude as well. This also includes altitude information. So these are the 4 main parameters that determine how big this footprint is. So if you have less velocity, that means you have less energy. Therefore, you will have a smaller footprint because you can't fly as far. You don't have as much energy to stretch into downrange. So you can kind of think of it like the following, that energy is your money. You have energy when you're coming back. And you eventually have to spend all of your money so that you end up with $0 left once you get to the target at the very end. So you have to figure out, well, how should I spend my money? How should I spend my money? So should you spend a whole bunch first and then barely survive to the very end? Or should you spend very little at the beginning and then spend a whole lot to make sure you get to the end? Or should you try to do it evenly throughout? This is kind of the challenge. And so, as I was saying earlier, the footprint is shrinking. And the point that it shrinks towards is actually located on the edge. So, like how I was saying up here, if you're flying full lift up, your point that you're aiming at is right here on the edge of the footprint. Correspondingly, if you are flying, say, a 30-degree bank angle, so if here's your vehicle, oh, that was bad. If here is up and here's your lift vector, you're flying at 30 degrees, you'll be coming in, say, probably right here at this point. So as you fly in, turns out your footprint starts shrinking towards this point on the edge, and I call this point the aim point. The aim point. So as you are flying in, you're draining off your energy because you are hitting the atmosphere and slowing down, which means you have less energy. But in the time that you're doing that, you're getting closer and closer. So what's happening is if you compute a new footprint, it'll look something like this. That all of these sides are collapsing towards this one point that you're aiming at right here. So everything falls towards this point. So if we keep flying along just like that, then we'll end up with a new footprint that looks something like this. And pretty soon we'll see, oh, well, we got to be careful because if we don't, change our current aim point, which we're aiming right here, our target might fall out of our footprint. So we would say, okay, well, now instead of aiming right here, let's aim, we're still aiming on the edge of the current instantaneous footprint. So let's aim right here. So let me zoom out so we can start with a clean picture. So the yellow line is the current footprint. Here's the target. And let's start aiming here at this location. So as we do that, then you can see, well, the footprint starts shrinking towards this location. So now it starts looking like this. And then we keep flying there, and then it starts looking like this. And so you can see, you could really frame the problem of getting to your target as keep the target inside the footprint. So what this means is you need to keep changing the location of your aim point on the edge of your instantaneous footprint so that you can keep your target inside the footprint as long as possible. Now, before I finish here, I want you to think about this. Will you be able to keep the target inside your footprint the entire time? All right, think about that and then come back and I'll see you in the next video.